This video will be focusing on part 1 of solutions, which is essentially discussing what are solutions, what are they composed of, and how can we determine if something is soluble or not soluble. So those are the two, and also electrolytes. So those are the three major topics that we will be discussing in this particular video. In the following video, which will be part B for this chapter, we'll talk about different units for concentration of a solution and why the concentrations are important. Okay, so let's begin. So the first thing is, what are solutions? What is the definition of a solution? So solutions essentially are homogeneous mixtures of two or more substances. So when they're mixed together and it forms a homogeneous mixture, homogeneous meaning it is uniformly distributed. All the substances that are mixed together are uniformly distributed throughout the solution. That type of a mixture is called a solution. So this is formed when there is enough force of attraction between the solute and the solvent molecules to keep it together. So those are solutions. For instance, if we take salt and we dissolve it in water, and as long as the salt is completely dissolved in water, that would be an example of a salt solution. Whereas if you take sand and you disperse it in water, it is not going to dissolve in water. It will be not a homogeneous mixture. It will be just a simple heterogeneous mixture. That is not something that we can call as solution. A solution has to be homogeneously mixed all over. Now, regarding solutions, the composition of a solution, it basically consists of two major components. One is called the solute and the second is called the solvent. Solute is the substance which is present in the lesser amount. That's the very simplest definition of the solute. Solution is composed of solute and solvent, and solute is the one which is present in the lesser amount, whereas the solvent is the one which is present in higher amounts. So this is higher amounts, and solute is the one which is lesser in quantity. Okay, now, here it's giving you the same definition again. Solute is the substance in smaller amount and the solvent is the substance in greater amount. Now when we talk about solutions in total, they can be of many different types, and that would depend on what solute and what solvents we are mixing together. So for instance, solute can be liquid, gas, or solid. Whenever we talk about solution, we usually think we are mixing a solid into a liquid, but that's not true. Solute can be liquid, gas, or solid. They are spread evenly or uniformly throughout the solution. Solutes mix with solvents so that the solute and solvent have the same physical state. What this means is that in the beginning, solute and solvent can be of different states, but at the end, once a solution is prepared, both of those are in the same state. For instance, if we make salt solution, usually salt, which is NaCl, if you're making this at home, NaCl is the normal salt that we have, that is usually solid, whereas water is usually in liquid state. But when they are both mixed together and the salt is completely dissolved in water, they both are present in the same state. For instance, if this is salt solution, they are present in aqueous state. So at the end, solution has the in case of a solution, both solute and solvent will have the same physical state. And the important thing is that once the solution is prepared, we cannot separate the salt from water anymore just by filtration. Okay, so separation cannot be just a physical process. Solutes cannot be separated by filtration, but they can be separated by evaporation. So simple example is a salt solution. If you want to separate salt out of this water, you cannot pass it through a sieve or a filter paper, but only way you can separate them is probably doing heating this water solution up. Once it's heated, all the water vaporizes and the salt is left behind. The solutes are not visible, but they can give a color to the solution. So once the salt solution is completely made up, all the salt is dissolved, you can tell that you can't find the solute anymore. You cannot see the salt crystals anymore. Only thing you can see is that it looks a little bit turbid in color, right? So it can give it a certain amount of color, but usually it's not visible. So when we talk about different types of solutes and solvent, like I said, solute and solvent can be in multiple different states. For instance, their solutions can be gas solutions, meaning we have our gas and gas. Our solute is gas and our solvent is also gas. One example of that is air. Air is a homogeneous mixture of oxygen, nitrogen, hydrogen, helium, all those gases. So this is an example of gas in gas solution. Here the solvent would be the one which is highest amount, meaning nitrogen gas, and solute can be, for instance, oxygen here. Okay. Liquid solutions could be where basically our final solvent is liquid, but your solute could be gas. So meaning it's a solution of gas and liquid. Gas and liquid example would be one common example that we use at home, soda water. What is it composed of? It has CO2 gas mixed in with water. So that is an example of gas in liquid solution. Liquid in liquid, fairly simple, vinegar. Vinegar is basically acetic acid. This is the chemical formula for vinegar. So this is the solute mixed into water that gives us dilute vinegar that we can consume. So this is an example of liquid in liquid. Solid in liquid, one easy example is seawater, which is salt dissolved in water. So here water being the larger amount is the solvent, NaCl is the solute. Next would be solid solution. So we usually think, like I said, solutions would be liquids, but that's not true. Solutions can be solid as well. As long as it's a homogeneous mixture, it is a solution. For instance, solid in solid would be alloy. For instance, brass. Brass is composed of both zinc and copper metal mixed together. So both of those are solid, and after finally mixing, that solution is also a solid, which is called brass. Similarly, another example is steel, which is a mixture of carbon and iron. So solutes and solvents can be solid, liquid, gases. It doesn't really matter. Okay. One very common rule that we can talk about, or rule of thumb in terms of solutions, is that like dissolves like. Like dissolves like, meaning like interacts with something that it is something which is similar to it. For instance, here when we say like, we are specifically talking about polarity of a molecule, a property of a molecule, which is polarity. Now when we talk about polarity, we can classify the compounds as either polar or non-polar. So what this rule tells us, that if you're mixing polar molecules, like dissolve like, that means polar mixes with polar molecules, and similarly non-polar molecules mix with non-polar molecules. But if you try to mix polar with non-polar, that is not going to mix. Why? Because again, like dissolves like. Only like compounds like each other, they are going to mix with each other. For instance, if you try to mix salt in water, so salt in water is an example of polar mixes with polar. Salt in water, that would mix. Whereas if you try to mix oil in water, that is not going to mix. That will not prepare a solution. Why is that? Because oil is non-polar molecule and water is a polar molecule. So if you try to mix unlike molecules together, for instance, non-polar solute mixed with polar solvent, solution will not form. Similarly, if you do vice versa, your solute is polar and solvent is non-polar, the solution will not form. Only like molecules dissolve or mix with each other. Unlike molecules do not. Here, oil is non-polar, water is polar, so they are unlike molecules. But if you mix polar molecule with polar solvent, non-polar solute with non-polar solvent, they will mix with each other. Okay, for instance, if you take polar with polar, let's say a salt solution. So salt is a polar molecule, which is our solute. Solvent is water. Water is also a polar molecule. So polar and polar will make a solution. Non-polar and non-polar will also make a solution. For instance, if you take olive oil and mix it with grapeseed oil, those two oils, both the oils are non-polar, so they will mix with each other. So that is an example of like dissolves like, and unlike molecules don't mix with each other. Okay. Moving on, one quick question or would be, why is water such a good solvent? So if you think of solutions, most of the times what comes to our mind is something dissolved in water. So why do we always think of water as a solution, as a part of a solution? Because water is a very good solvent. Why is that? First thing, we know water is a polar molecule. Okay. The next thing we know, it can make hydrogen bonds. So hydrogen, in case of water, remember hydrogen bond is whenever hydrogen is bonded to a molecule of oxygen, fluorine, or nitrogen, that hydrogen can make a hydrogen bond. So in case of water, so water usually forms whenever any other molecules are added into water. Most of the times those molecules can form hydrogen bond with water, or that basically helps those other molecules to dissolve in water. So any polar substance or ionic compounds can basically make interaction with water, and that's why water is a very good solvent. One, it is a polar molecule, because you know that in case of water, we saw in Lewis structure, the shape of water would be essentially a bent shape. So dipoles don't cancel, therefore it's a polar molecule. Second thing we know is that water can form hydrogen bonds, which is very important in basically all the biological processes that happen. Water plays a very important role in there, and one of the very important feature of water is that it can form hydrogen bond with each other. And if we dissolve certain compounds into water, if they also consist of a hydrogen like this, they can form a bond, hydrogen bond with water as well. That makes water a very good solvent. Okay, now we'll talk about how actually does a solute dissolve in water. So for instance, if we take example of NaCl in water, salt in water, how does it actually dissolve? Why does it slowly disappear in salt? Okay, so what happens whenever solute, for instance an ionic compound, is dissolved in water, that ionic compound usually forms is each atom of that ionic compound is separated from each other, and water surrounds that ion, which is called the process of hydration. Okay, so this process where ionic compounds dissolve in water is called the process of hydration, where each atom of the ion, for instance NaCl, each atom, meaning Na plus Cl minus ion, they interact with water and they are surrounded by water, and that process is called hydration. How does this actually happen? So for instance, if we say this is a crystal of NaCl where we have bunch of atoms of Cl, which is the green one, and bunch of atoms of Na, which is the purple ones. So water, we know, has a charge. It's a polar molecule because there is oxygen and then there are two hydrogens attached to it. And because of the electronegativity of oxygen, we know oxygen carries a partial negative charge and these hydrogens carry a partial positive charge. So when this crystal is dissolved in water, whatever atoms are on the edges or the surface of this crystal are going to interact with water first. Whatever is on the inside of the crystal stays inside, but whatever is on the surface interacts with water. So if there is a positively charged if there is a positively charged atom, like here, this is the sodium atom, it has a positive charge. So water, the oxygen atom on water has a negative charge. This negatively charged oxygen is going to interact with this positively charged sodium ion and slowly going to take it away from the rest of the crystal. And now this sodium will be surrounded by water, such that these red atoms that you're seeing are all oxygen. Oxygen will interact with this positively charged ion because oxygen carries a negative charge, and so sodium ion is separated. Similarly, the chloride ion, for instance right here, which is present on the surface of the crystal, is going to interact with the hydrogen atoms of the water molecule, because hydrogen carries a partial positive charge whereas chloride carries a negative charge. So these partial positively charged hydrogen atoms are going to interact with chloride ion, and they are going to separate the chloride ion from the crystal, and they will be surrounded with these hydrogen atoms of water surrounding it, and chloride will be separated. So basically we start from the surface of the crystal, and as we go into the crystal, each water molecule interacts and separates the ion until all of this crystal is completely dissolved. So basically each water molecules basically are pulling each ion away from the crystal and hydrating each of them separately. Once all of these are dissolved, then you don't see the crystal anymore. So that is how exactly an ionic compound dissolves in water. The ions on the surface of the NaCl crystal are pulled into the solution and surrounded by water in the process called hydration. This process keeps on happening until all the NaCl is completely dissolved, and hydration of the ion diminishes their attraction to other ions and keep them in solution. Now basically this Na is surrounded by water. Similarly, this chloride is surrounded by water. So the force of attraction between Na and Cl minus is now reduced. Okay? So that is exactly how an ionic compound dissolves in water. And for a covalent compound to dissolve in water, water is going to form hydrogen bond with that with the hydrogens that are present in the covalent compound, and that would help in solubilizing those covalent compounds into water. Okay. Now solution with non-polar solute. If you are making non-polar solute with water like a polar solvent, they are not going to interact. There will not be any force of attraction between the particles of a non-polar solute and a polar solvent, and that is why non-polar solutes will not mix with polar water molecules. Okay. So in order to mix non-polar solutes or dissolve non-polar solutes into a solution, we need non-polar solvents. Okay. Let's try a couple questions. Identify the solute in each of the following solutions. So we have to figure out what is the solute in this solution. Solute is the one which is in lesser quantity, and solvent is the one which is in larger quantity. So we have 2 grams of sugar, 100 ml of water. If you know, water has a density of 1 gram per ml, which means 1 ml of water weighs 1 gram. So if here we have 100 ml of water, that means we have 100 grams of water, because you can't compare apples to oranges. If you're comparing grams, we have to compare it to grams. Okay. So in this case, we have now 2 grams of sugar, 100 grams of water. Which one is lesser? Sugar. So here sugar is our solute. 60 ml of ethyl alcohol and 30 ml of methyl alcohol. So which is lesser quantity? Methyl alcohol. So that is our solute. 55 ml of water and 1.5 grams of NaCl. Again, here if we have ml in grams, so easiest way is to convert water into grams. So 55 ml of water would mean this is 55 grams of water. So again, in this case, the lesser quantity is NaCl, so that is our solute. In case of air, we have 200 ml of oxygen and 800 ml of nitrogen. Oxygen is less, so that is our solute. Next, when solid LiCl is added to water, it dissolves because the Li plus ions are attracted to oxygen atom of the water or hydrogen atom of the water. Again, LiCl is a salt. It's ionic compound. It consists of 2 ions, Li plus and Cl minus. Li plus has a positive charge, so it will be attracted towards the negatively charged atom. So answer is going to be 1. It will be attracted towards oxygen atom, which has a partial negative charge. Similarly, the chloride ions will be attracted to the positively charged hydrogen atoms of water. Okay, the next topic we'll talk about are electrolytes. Whenever we talk about salt solution, one very common terminology that is used is electrolytes. And what is an electrolyte? It is a substance that can produce electrically conducting solution when dissolved in water. So basically, electrolytes are the solutions that can conduct electricity. The solutes that can, when we dissolve them in water, they are going to be good conductors of electricity. That is why they are called electrolytes. So if we talk about when somebody is like not feeling well, they have a fever, or somebody is getting dizzy, we usually talk about that they should consume more electrolytes. Why is that? Because in our body, electrolytes regulate our nerve and muscle function. Electrolytes are very important. They control the hydration in case of our body. They control what is the pressure of our blood. They control which reactions, which chemical reactions will happen in our body and which will not happen in our body. Therefore, maintaining the level of electrolytes in our body is very important. Okay. So what are electrolytes? When we drink electrolytes, if you have ever seen the composition of those electrolyte solution, they majorly consist of ions. Ions like sodium ion, potassium ion, chloride ion, bicarbonate ion. Those are the major types of ions that make up the electrolytic part of our uh, body solutions. Okay. So that's why they say sometimes you should just drink some salt solution, right? Because it consists of sodium and chloride ions. So an electrolyte is very important to maintain the level of the electrically conducting solutes in the blood. Okay. So now when we say electrolytes, there can be two different types of electrolytes. One is a strong electrolyte, another one is a weak electrolyte. What do electrolytes do? Electrolytes essentially dissociate in water. Dissociate means they break apart. For instance, if we take NaCl, which is solid, and we add it to water, it is going to dissolve and dissociate, meaning separate from each other to form Na ion, which is now aqueous, and Cl minus ion, which is now aqueous. So this process is called dissociation. Strong electrolyte basically will completely dissociate in water. So for instance, if you take a spoon of NaCl, you add it to water, a cup of water, that one spoon is going to completely dissolve into ions. That when something completely dissolves into ions, that is called a strong electrolyte. They usually can conduct an electric current very strongly. Weak electrolytes only dissociate slightly. For instance, if you take this HF into water, it will dissociate. HF is going to break apart into H plus and F minus, but at the same time, not all of it is going to dissociate. Some of it is going to still stay as HF. Those are called weak electrolytes. Such solutions are called weak electrolyte solution because there not all the salt has completely dissociated into its ions. They slightly dissociate in water and they would also conduct electricity but not as strongly as the strong electrolytes. So those are called weak electrolytes. And then there is something which is called a non-electrolyte. A non-electrolyte would be a compound which basically does not dissolve in water. It does not produce ions in water. It is not going to conduct any electricity. For instance, if you take sugar and you dissolve it in water, sugar is called sucrose, is the chemical name for sugar that we eat, cane sugar in our house. So if you take sugar and dissolve it in water, it will dissolve, but it is not going to produce any ions because this is not an ionic compound. So it is, as there will be no ions in the solution, it is not going to conduct any type of electricity. So those are examples of non-electrolyte solutions. They do dissolve in water, but they don't have any ions. They cannot conduct electricity, so they are not electrolytes. They are non-electrolytes. So let's try some questions. Complete each for a strong electrolyte in water. So if the question is telling you this is a strong electrolyte, it means it is going to completely dissociate into its ions in water. So calcium chloride solid in water is going to give us, it's a strong electrolyte, meaning it will completely dissociate into its ions. The two ions would always be a cation and an anion. Here the ion is calcium ion. Calcium, it always makes its group number 2, so it will always be calcium 2 plus, and chloride is group number 7, so it will always be 8 minus 7, which is a -1 charge, and this would also be aqueous. And you can see each calcium chloride has 1 calcium ion and 2 chloride ions, so this would be 2 chloride ions. And remember, ions are always aqueous in solution. Like we saw before, ionic compounds dissolve in water and they get hydrated, so they have, each ion has water molecules surrounding it, and that is why it is called aqueous. The state now is called aqueous. So your answer here is going to be C. Next we have K3PO4. Again, the question is, it's a strong electrolyte, so you don't have to think this too much. Only straight answer is that it is going to dissociate into ions. What ions does this have? It has potassium ion, and it consists of this PO4 minus. Remember, it's a polyatomic ion, so PO4 3 minus is the phosphate ion. How many potassium? I see 3 potassium, so 3, and phosphate stays together. We only have one of those, so it will be 1 phosphate ion, and each ion is going to be hydrated, so they will be aqueous. So answer here is going to be A, 3 for potassium and 1 phosphate. Do not break phosphorus and oxygen apart from each other. This is a polyatomic ion. It always stays together. Next kind of question could be like this. Which of the following reaction represents the dissociation of a strong electrolyte and water? Again, we are looking for a strong electrolyte, meaning it will dissociate to give ions completely. And what you're seeing here in the first reaction, there is no dissociation happening. The products are not ions. Same thing in reaction number B. This is methanol in water. It's still methanol. It is aqueous, but it's not ionic in nature. Until it's ions, it is not going to be an electrolyte. It has to be ionic. Products have to be ions at the end. D is again an alcohol, but it is not dissociated. It is not ions. We don't see ions in products. Whereas for part C, we do see ions. Sodium sulfate dissociates to give 2 sodium ions and 1 sulfate. So answer is C. Next, write the equation for formation of a solution for each of the following. Now it's telling you to write a reaction, chemical equation for this. The dissociation of K2CrO4, which is solid, a strong electrolyte. So it's telling you it is strong. So you can simply break this into 2 ions. So this would be K2CrO4 solid. It will dissociate in water, which is liquid, to give us potassium ion. Again, this is 1 ion and this is a polyatomic ion. So CrO4 2 minus. This will be aqueous. This will be aqueous as well. How many potassium? 2. Now, one question you could ask me, how is this -2? How did I know that? Again, first thing, you should be able to identify it's a polyatomic ion. Next thing, we can assume, if we don't know the charge, you could calculate the charge, just how we have been doing before when naming these compounds. So for instance, potassium always carries a charge of +1. And how many of these atoms do we have? 2. So 2 times +1, plus we'll assume the charge of this whole anion is X. And total charge, sum of everything, is equal to 0. Why 0? Because the compound is not charged. It's a neutral compound. Now we solve for X. So if you solve for X from this here, it would give you X is -2. That's how I know this is -2. Otherwise, if you have memorized this polyatomic ion, you would know it always carries a charge of -2. Okay, moving to part B, which is the partial dissociation of a weak electrolyte, H3PO4, in water. Question is already telling you it does not completely dissociate, it partially dissociates, and it's a weak electrolyte. So we will start with our compound, which is H3PO4. In water, it is going to give us hydrogen ions, which would be 3 hydrogen ions, because we have 3 of those, and 1 phosphate ion, which is PO4 3 minus. But since it's a weak dissociation, you would show this as a double-sided arrow. It will convert, some of it will convert into proton and phosphate, whereas some of it will go back into its actual H3PO4 formation. So this, When you put a double-sided arrow, that you're showing it is going both ways. It is a partial dissociation. Not all of it has completely dissociated. Next is dissolving of solid sugar in water. Now, when you look at this molecule, this is not a ionic compound. So when you see that something is not ionic, you basically will only dissolve this in water. If this is solid in water, it is going to become, it will dissolve, and once it dissolves, it will become aqueous, but it will not dissociate. You can't break this into ions. So this is a example of non-electrolyte solution, which you, of course, the question is not asking for that, but the question is only asking for this particular reaction. Okay. All right. Now moving ahead, when we talk about electrolytes in our solution, in our body, in the fluids in our body, how do we measure how many electrolytes are present? What is the measure of those number of electrolytes? They are usually measured in terms of equivalence. Okay, equivalent, each ion gives one equivalent. Every single, the charge of the positive ions and the amount, basically the amount of ions that are present in a compound is called as equivalent, and each charge, each positive and each negative charge gives one equivalent. Okay, each electrical charge is regarded as one equivalent. For instance, if we talk about sodium ion, one sodium ion carries a charge of +1. So its ionic charge is 1, meaning the number of equivalents it will produce in 1 mole would be 1 equivalent. Okay, so 1 equivalent is the amount that ion equal to 1 mole of positive or negative charge would produce. So if we say ammonium ion, ammonium is NH4 plus. Since the ion carries a charge of +1, it will produce 1 mole of this compound will produce 1 equivalent of charge. Calcium ion carries a charge of +2, so its ionic charge is +2, which means 1 mole of calcium ion would produce 2 equivalents of charge. Okay, so whatever is the charge on the compound, that is how many equivalents it is going to produce in 1 mole. Iron 3 plus has a charge of +3, so it will produce 3 equivalents. 1 mole of iron will produce 3 equivalents. So equivalence essentially means how much electrical charge can each mole of this molecule produce. It can be positive or negative. For instance, this ion, carbonate, CO3 2-, each ion, anion, has a charge of 2-, so it will produce 2 equivalents. Chloride ion has a charge of -1, so 1 mole of chloride would produce 1 equivalent. Phosphate ion has a charge of -3, so each mole, 1 mole of phosphate would produce 3 equivalents, and we can use this as a conversion factor, meaning I could say that 1 mole of sodium ion is equal to 1 equivalent of charge. Okay, similarly I can say 1 mole of chloride ion is equal to 1 equivalent of charge. 1 mole of phosphate ion is equal to, charge is 3, so 3 equivalents of charge. And you could use this as a conversion factor for any type of question that is asked. For instance, if we talk about this question, the lab tests for a patient indicate a blood calcium level of 8.8 milliequivalents per liter. How many moles of calcium ions are present in 0.5 liter of blood? So what is given to me? The information that is given to me in question is that we have 0.50 liters of blood, and it is telling me, so let me write it here, what is given to us is 0.50 liters of blood, and the question is asking to convert this into moles of calcium. Okay, and it has given us the calcium level of 8.8 milliequivalents of calcium per liter. Whenever you see this given to you in question, that means this is a conversion factor. let's convert it into a conversion factor. We can say that 8.8 milliequivalents of calcium ion is equal to 1 liter of blood. Why? Because this is telling you that indicate a blood calcium level of these many milliequivalents per liter. So 1 liter of blood has these many milliequivalents of calcium. So now we have a conversion factor between milliequivalents of calcium to liters of blood. Okay, so how can we go from this to moles? Another conversion factor that we know of when we talk about milliequivalents and moles is that 1 mole of calcium ion is equal to 2 equivalents. So this is one conversion factor. This is the second conversion factor that we know of. Now we have to figure out how to relate these conversion factors. So always find the common factors in between them. So for instance, what's given to us is liters of blood. Do you see liters of blood anywhere here? I see liters of blood here. And I can convert these many liters into milliequivalents of calcium. Once I have milliequivalents, do you see another relationship? Does it have equivalence anywhere? It has equivalence here. What I will get from this conversion factor is milliequivalence, but milli can be related to equivalence by another conversion factor, which is 1 milliequivalent, or 1000 milliequivalents is equal to 1 equivalent. We know the relationship between milli of anything. It's 10 raised to power 3. So I can then go from milliequivalents to equivalents, and then I can go from equivalents to moles of calcium. So our conversion factor would here basically have multiple steps in between. We can go from liters of blood to milliequivalents of calcium using this. Then from milliequivalents, I can go to equivalents of calcium using the top conversion factor, which is 10 raised to power 3 milliequivalents equals 1 equivalent. And then from equivalent, we can go to moles of calcium by using this conversion factor, which is 1 mole will produce 2 equivalents. So let's start from here. You could do this in different steps or in one step. I'll show you the answer done in one single step following this solution map. So we'll start with what's given, which is 0.50 liters of blood. I want to cancel the liters and convert it into milliequivalent, so I can be right here. So we divide by liters and multiply by milliequivalents of calcium. We know 1 liter is 8.8 milliequivalents. Liter and liter is cancelled. We are left with milliequivalents. Now from milliequivalents, we can go to equivalents, which would be to cancel milliequivalents and convert it into equivalents of calcium. And we know that 1 equivalent is 1000 milli. So this and this is cancelled. I'm left with equivalents. Now to cancel equivalents, I'm going to convert these equivalents to moles using this. So to cancel equivalents, I divide by equivalents and multiply by moles of calcium ion. So, and here we know that 1 mole of calcium is 2 equivalents. So this and this will be cancelled. What we are left with is 0.50 times 8.8 divided by 1000 divided by 2. And our final answer is moles of calcium ion. So if you plug this into your calculator, it will give you your final answer as 0.0022 moles of calcium. Okay, this should be moles actually. Okay, so the final answer is 0.0022 moles of calcium ion. So basically, if this information is given to you, you can convert it into a conversion factor. Previous question we saw is more like a tricky question that you might not see a lot, especially not in the exam, but that is how you could use conversion factors essentially. Okay, the type of questions you can expect is like this. So in 1 mole of iron 3 plus, there are how many equivalents? Each mole of iron would have 3. It has a charge of 3 plus, so equivalents would be 3. In 2.5 moles of sulfate, there are how many equivalents? So what's given to us is moles of sulfate, and the question is asking to convert these moles of sulfate to equivalents. What is the relationship that we can use here? Moles of sulfate to equivalents. The relationship for sulfate is, we know that 1 mole of sulfate is 2 equivalents because it has a charge of 2 minus. So if we use this conversion factor, we start with moles, 2.5 moles of sulfate. I cancel the moles, so I divide by moles and multiply by equivalents, which is EQ. 1 mole is 2. So basically your answer would be 2.5 times 2 equivalents, which is 5 equivalents. Next, we have an IV bottle contains NaCl. If sodium ion is 34 milliequivalents, what would be the total amount of Cl minus ion? Remember, the total positive charge should always be equal to total negative charge. So if it is 2 equivalents of positive, the negative equivalents also have to be equal to 2 equivalents. Okay. So in this case, the sodium ion brings the positive equivalence, which is 34. So chloride ion will also bring the same amount, which is 34 milliequivalents per liter. It has to be, the total charge has to be cancelled out. The final charge should be 0. So the amount of positive charge and negative charge should always be equal to each other. Since both of them have 1 charge, they will be same number of equivalents. Okay, the next topic we'll talk about is solubility. What does solubility mean? So for instance, if you take a cup of salt and a cup of water, a small tiny cup of water, and you start adding sugar into it or salt into it, NaCl into it, you will add 1 cup, 1 spoon, 2 spoon, 3 spoon, 4 spoon. At some point, no more salt will dissolve in that water, right? And that is exactly what solubility tells you. It tells you the amount of solute that can be dissolved in a specific amount of solvent. So this tells you how much solute, maximum amount of solute that we can dissolve in a certain amount of solvent. For instance, if you take NaCl, you add like 4 spoons, 5 spoons in a cup of water, and then it would stop dissolving. That means 5 spoons can be maximum dissolved in 1 cup of water. So that would be solubility of water. Salt in water. Okay, and now if I take the same cup of water and I heat it up, now maybe it's possible that I would be able to dissolve, instead of 5 spoons, I might be able to dissolve maybe 7 spoons of salt into that. Why? Because now the water is heated up, so molecules have more energy, and because of that they would be able to move around more, and we would be able to dissolve more solute into that solvent. Same amount of solvent can hold more solute. So when we talk about solubility of a solution, that is temperature dependent. As long as you're not changing the temperature, the solubility will stay same. But if we change the temperature, the solubility will also change with temperature. It's usually expressed as grams of solute in 100 grams of solvent. For instance, when we talk about solubility of potassium nitrate in water, it is given by 65 grams in 100 grams of water. This essentially means you could dissolve 60 grams of potassium nitrate in 100 grams of water. So basically I can use this information as a conversion factor now. If I have 65 grams of potassium nitrate, it will dissolve in 100 grams of water. So I can use it as a conversion factor to go from grams of potassium nitrate to grams of water when we talk about solubility. Okay. For instance, here if we want to figure out how many grams of water, how many grams of potassium nitrate can I dissolve in 120 grams of water, what can we do? We start with what's given, which is 120 grams of water, and we want to cancel the grams of water, so we divide by grams and convert it into grams of potassium nitrate. Now we use our conversion factor. Potassium nitrate is 65, water is 100. So here we can figure out how much potassium nitrate can you maximum dissolve in 120 grams of water. So this would give you an answer of 78 grams of KNO3. So basically this conversion factor of solubility will tell you how much amount of solute can you maximum fit into a certain amount of solvent. Now let's talk about different types of solution based on their solubility rule. Okay, so based on solubility, we can have different types of solution. For instance, unsaturated, saturated, and supersaturated solution. Okay, so let's take some example. For instance, I have this cup of water, like we used before. If we have 1 cup of water and we are adding salt into it, we said that the solubility of salt in this water is, let's say, 5 spoons in 1 cup of water. If this is the solubility of our solution, salt solution, and I start with 1 cup of water and I add 2 spoons into this, and that 2 spoons of salt into this, and that salt completely dissolves. Now this solution is called an unsaturated solution, where I have not reached the maximum amount of solute that is possible. Maximum I can add 5, I've only added 2 yet, so this is a solution of unsaturated salt solution, when your amount of solute is less than the maximum amount possible. Now let's say I take again this cup of water and I add 5 spoons of NaCl into it. This kind of solution is called a saturated solution, where we have added the maximum amount of solute into the solvent. So if I add another spoon of NaCl into this, it is not going to dissolve. That is called a saturated solution. It consists of the maximum amount of solute that can dissolve in there. Next type of solution is, let me take this solution. I will add 6 spoons into this. 6 spoons of NaCl into 1 cup of water, but I know it will not dissolve. So what I do, I heat this solution from to increase its temperature. Once you heat this solution, it is quite possible that all 6 spoons might dissolve into this, and this solution is now called a supersaturated solution. I dissolve 6 spoons and then I let it cool down. This solution is called a supersaturated solution. When a saturated solution is cooled down, it would consist of more solute than the solubility would allow. So at a room temperature, basically it can maximum hold 5 spoons. What I did is I added 6 spoons, I heated it up, it dissolved 6 spoons, but now I am cooling it down. So when you cool it back down, it consists of more amount of solute that it can actually hold, and that solution is called a supersaturated solution. Okay. Type of questions: identify each of the following solution as saturated or unsaturated. Which of these solution is saturated? Salt disappears when we put it in water, which means it is still unsaturated. We are adding it and it is dissolving, so we have not added the maximum amount yet. Sugar added to a cup of water does not disappear but sits at the bottom of the cup. So you try spinning it, you try shaking it, you try mixing it, it does not disappear, which means the solution is already saturated. It would not dissolve any more sugar. Okay. Another question is, at 40 degrees Celsius, solubility of KBr is 80 grams in 100 grams of water. Identify the following solution as either saturated or unsaturated, which means at 40 degrees, you can maximum put 80 grams of KBr in 100 grams of water. So if I have 60 grams of KBr added to 100 grams of water, I have not yet added the maximum amount possible. It is less than maximum, so this solution is unsaturated. Next, we have 200 grams of KBr added to 200 grams of water. If now I've added how much? 200 grams of KBr in 200 grams of water. If I try to convert these 200 grams of water, because right now the conversion factor that I have is based off of this. So now if I want to convert this, let's say if in 200 grams I have 200 grams of KBr, in 100 grams, If I divide this by 2, divide this by 2, I have 100 grams of KBr, which means I have added more than the maximum amount that is possible at that temperature. So this solution is going to be a saturated solution. 80 grams of it will dissolve, the rest 20 grams extra is going to sit at the bottom. Lastly, we have 25 grams of KBr added to 50 grams of water. So which means we have added 25 grams of KBr in 50 grams of water. But the solubility that I have is out of 100 grams. So if I multiply this by 2, that would give me 100, which means I multiply the above numerator by 2 as well. So that would be 50 grams of KBr in 100 grams of water. So right now in 100 grams, I only have 50. I can maximum have 80. So I have less than the maximum amount, which means this is also an example of unsaturated solution. So here basically I'm trying to make it equal to 100 grams, amount of solvent as 100, so I can figure out how much solute can be added. Okay, next we'll talk about what is the effect of temperature on solubility. Like we saw before, whenever we have a solid, when you try to add a solid, for instance, you take salt, NaCl in water, you heat it up, it is going to increase solubility. You can take another example, glucose is a sugar. You add the sugar into water, it has a low solubility, but as you increase the temperature of water, more and more sugar will dissolve in water. This is temperature, this is the amount that is dissolving. So if you take NaCl, Na3PO4, it's a salt. Slowly, it's a solid. So as you add it, as the temperature of the solvent or water is increased, more and more of it will become soluble, right? So most of the solid, solubility for most of the solid increases as the temperature increases. But now, in case of solids, the effect is this. In case of solids, temperature increase result in increase in solubility. But gases behave different. For instance, if you take a can of Coke and you leave it at the room temperature and you open it up, leave it at room temperature, and then you have the same can, we open it up and put it in a pan and start heating it up. Or you put it outside in the sun. Which one is going to get flat first? The one that is put outside, the one that is in heat. Why? Because gas, as we increase the temperature, those gas molecules are going to escape. As you increase the temperature, the gas molecules will have more energy. They are going to escape the solution. So the amount of gas in water is going to decrease, which means the solubility of gas in water decreases as we increase the temperature. So gases have an opposite effect. As we increase the temperature, the solubility decreases in case of a gas. Okay, and simple example is, you could take example of a can of soda. Okay, so simply take the soda bottle and can or bottle, you put it outside in heat, it is going to get flat first, but if you keep it on ice, let's say, it is going to take longer for this bottle of soda to lose all the carbon dioxide. So that explains the effect of temperature on solubility of a solution in when the solute is solid or when the solute is gas. Gases decrease as the temperature increases. Okay, so questions that answers can be explained based on this is, why would a bottle of carbonated drink possibly burst when it is left out in hot sun? Why would that happen? So if you have a bottle of carbonated drink and we put it outside, it consists of this gas dissolved in water. As the gas molecules gain energy, as the temperature increases, gas molecules, they are going to gain energy. More energy means more kinetic energy. More kinetic energy means they move around more rapidly. As they move around, they collide with each other and they collide with the bottle that they are kept in, which means it is going to increase pressure inside. Increase the pressure of gas inside the bottle. and that would cause it to explode. When it becomes unbearable for the bottle to keep the gas in, keep the pressure, it is going to explode. Next question could be, why do fish die in water that is too warm? Why? Because again, gases, solubility of a gas. As the water gets hot, solubility of gases in water. Gases in this case is, we are talking about air in water, decreases. Why? Because gases have more energy now, they are going to escape from the water. So solubility decreases, which means now fishes would have less of that air to breathe, which means they would die. Why does a cup of hot water dissolve so many more teaspoons of sugar than a cup of iced water? Why? Because when we increase the temperature, the solubility we saw of solid increases. Solubility of solids increase. So we could dissolve more of those solids into our cup. Okay. The next, over here we were talking about solubility with respect to temperature. How solubility changes when we change temperature. Next, we'll talk about how solubility changes when we change pressure. This is explained by Henry's law, which states that solubility of a gas in liquid is directly related to pressure of that gas above the liquid. At higher pressure, more gas molecules will dissolve in liquid. Okay, so Henry's law tells us at high pressure, more gas molecules dissolve in liquid. One quick example of that, you don't have to memorize it. It can be easily explained if you take example of a can of soda. So in case of a can of soda, when you open that can of soda, why is there that loud noise? That loud noise comes up because there is a lot of pressure that is present inside this can. Once we open that can, that pressure is released. Okay, so all that CO2 that is present inside this water is kept in. Why? Because that CO2 is under very high pressure. So when the pressure is really high inside the can, a lot of CO2 is dissolved in this soda water. But as soon as this is opened up, now this extra pressure gets released. So now this can of soda is under just simple atmospheric pressure. And because of that, that CO2, as the pressure above that can, above that CO2 soda has reduced, it is that CO2 which is dissolved inside that water is going to start escaping. It starts bubbling out of the solution. So fewer gas molecules are left in that can of soda. And that is exactly what Henry's law tells us. When there is a lot of pressure above the cola, the gas molecule stays in. But as the pressure is released above that cola by opening that can, less of the CO2 stays inside the water. So basically it tells us that at high pressure, the solubility of gas molecules in liquid is higher, and at lower pressure, the solubility decreases. Okay. Next, we'll talk about solubility. How do we know certain compounds dissolve in water and some compounds don't dissolve in water? So the compounds that dissolve in water are called as soluble compounds, and the compounds that do not dissolve in water are called insoluble compounds. Okay, so soluble compounds basically dissociate in water. For instance, NaCl, we saw NaCl will dissociate to give us Na plus ion, Cl minus ion, and it completely dissolves. Whereas insoluble compounds, they do not dissociate in water. They have a very low solubility. Only very small amount of it will dissolve. Most of it will stay as solid. So those are called insoluble compounds. How can you predict if a compound is soluble or not? This is the solubility chart, which can help you predict if an ionic compound is soluble or insoluble. Okay, usually you are expected to memorize this, but your exams are open book, so you could take a look at this chart and figure out if something is soluble or insoluble. But you should know how to read this chart. Okay, so everything that is listed in this chart is soluble, and exceptions are given to you alongside. So positive ions, when we talk about compounds that consist of these ions, all of them are insoluble, all of them are soluble. For instance, group 1 in the periodic table consists of lithium, sodium, potassium, cesium, rubidium. All of these are soluble compounds. If an ionic compound consists of these cations or these positively charged ions, all those compounds are going to be soluble. There are no exceptions. Same is true if we talk about a polyatomic cation, which is ammonium. All these compounds will always be soluble. Similarly, all the nitrates and all the acetates, this is an acetate. All nitrates and acetates are soluble irrespective of what is the cation in that compound. No exceptions. As long as it's a nitrate, it is soluble. As long as it is acetate, it is soluble. Similarly, all chlorides, bromides, and iodides are going to be soluble, but there are some exceptions here, which is silver, lead 2 plus, and mercury. So in this case, if it is silver chloride, it will be insoluble. If it is lead 2 chloride, that would be insoluble. If it is silver with iodine, all iodides are soluble except when it is with silver, when it is with mercury 2 plus or lead 2 plus. Similarly, all sulfates are soluble. Exceptions are barium, lead, calcium, strontium, and Hg2 2 plus. So if let's say if we talk about barium sulfate, that would be insoluble. If I talk about sodium sulfate, that would be soluble. All sulfates are soluble. Exception is barium, lead, calcium, strontium, mercury. Okay. And when something is not soluble, you guys have already seen those in precipitation reaction, those insoluble compounds usually form solids, and that solid is called as a precipitate. When you take two ionic solutions, mix them together, and it produces a solid, that is called a precipitate. For instance, if we ask you, can you predict what would be the products for this particular reaction? When you see a compound like this, you should know that this is an example of a double displacement reaction, something we have done before in previous video. So if you are not if you can't remember that concept, go back and look through the video of type of the reactions, type of chemical reactions. Okay, this is an example of double displacement where lead is going to now form a compound with sulfate. So this is composed of two ions, lead and nitrate. Now here lead is going to, and this is composed of potassium and sulfate. So this is our cation, this is the anion. This is the cation here, this is anion. So cation 1, anion 1. This is cation 2, anion 2. So cation 1 is now going to form a new compound with anion 2. And cation 2 is going to form a bond with anion 1. So now the products are going to be lead with sulfate. Lead is +2, sulfate is -2. So the crisscross charges will give us the compound of PbSO4. And the second compound it will form is potassium with nitrate. Potassium is +1, nitrate is NO3 to NO3 -1. So crossing over the charges would give us KNO3. Going back to this, lead was Pb2 plus and sulfate is SO4 2 minus. Crossing over the charges would give us Pb2 SO4 2, and we want the least ratio, so it will be PbSO4. Now the question is, what are the phases for these? Is it soluble? Is it not soluble? We saw in our solubility chart all the compounds that consist of potassium are soluble. All the compounds that consist of nitrate are soluble, no exceptions. So if it is soluble, it will be aqueous. PbSO4, we saw that all sulfates are soluble, but lead was an exception, meaning this will be solid. So now if you mix these two solutions together, they are both aqueous, meaning you can see they're liquid. When you mix two liquids, this particular solid will start appearing, and that solid is called a precipitate. So this solubility chart can help you predict what would be your reaction products. Okay, so here again, this is the same thing. Now, we'll quickly go through this. I will not be asking you much questions on this concept. Basically, the same reaction, ionic reaction, this is called, when you write the whole thing, this is called the chemical reaction. The same reaction, when you try to break it apart into its component ions, that would be called as ionic equation. When whatever electrolytes are present here, you dissociate those electrolytes. For instance, lead nitrate will give you lead ion and 2 nitrate ions. 1 potassium sulfate will give you 2 potassium, 1 sulfate. So 2 potassium ions, 1 sulfate ion, and all of those are aqueous because they are all ions. Ions are always aqueous. Will react to give us what? Lead sulfate. This is a non-electrolyte because it is solid. It does not dissolve in water. It does not dissociate. So it would be written as PbSO4. Potassium nitrate would give us 2 potassium ions, 2 nitrate ions. So you write this into ions. When you break apart each molecule into the ions that are possible, if it can be broken into ions, it would be called ionic equation. And out of this, whatever ions are common on both the sides of the arrow, if you cancel those out and write the leftover reaction, that is called the net ionic equation. What do I mean by that? For instance, if we look at nitrate here, nitrate, I have 2 nitrate ions on the reactant side of the arrow, and I have 2 nitrate ions on the product side of the arrow. So I can cancel these out. You cannot have a same compound as a reactant and as a product, right? Similarly, potassium ion, I have 2 potassium ions on the reactant, 2 on the product, so I can cancel those out. I have 1 lead ion here. On the product side, I don't have any lead, so I can't cancel that. Sulfate, I have 1. Again, I don't have it on product, so I can't cancel it. Lead sulfate, I have 1 on the product, none on the reactant, so I can't cancel it. So whatever leftover reaction is left, you rewrite that, and that is your net ionic equation, which would be lead plus sulfate would give us lead sulfate solid. This is called the net ionic equation because when you mix these things together, actual reaction that is happening is just this. Okay, and rest of the ions, they were present before the reaction, they are present after the reaction, they were present before, they are present after the reaction. These products or the reactants that do not change, that do not react, that do not produce a product are called the spectator ions, meaning they are just there during the reaction. They are just watching the other compounds, the other ions react with each other to produce products. They are actually just present there, just looking at other reactants react. So they are called spectator ions, and whatever left